Hey y'all, there's been some questions about when we would do the auto throttle switch pack cleaning procedure. Some of those events would be if the task card is assigned, 2, if we don't have a new auto throttle switch pack in stock, or we don't have the time to replace an auto throttle switch pack. That's when we would want to attempt cleaning procedure. Both the AMMs for the MAX aircraft and the NG aircraft both have the cleaning procedure in them. We can use the test box to check the switches to see if they're making and breaking cleanly, and also what the voltage drop is across the contacts for normally closed, normally open contact. When we use the cleaning procedure, what we're going to do is we're putting current through the switches as we operate the throttles or the reverse thrust lever. That procedure actually will clean the contacts in most cases. There will be some times when a switch pack needs to be replaced if the switch packs are not cleanable or cleanable to a suitable value. This will save tremendous amount of time and money if this procedure is done correctly, and we hope to mitigate out of service events by either putting the airplane back in service if there's no parts or we don't have the time to replace the switch pack.
Here we're going over the paperwork and making sure that everything's correct, and going in, making sure all the circuit breakers are pulled that you need to pull.
The B61 is Delta 13.
Got it.
B62 is Bravo 9.
Got it.
So right now you can see our engine performance control page. We do not have any power going to our EECs, which is why we opened up a second window.
Got to know it ain't no men.
Okay, so the first thing we want to do is we want to enter the onboard maintenance function by hitting the system button, and then we're going to select maintenance. Then we're going to go to maintenance control pages. What we want to do here to miscellaneous system controls, and what we want to do here is open up 2 displays. So we're going to go down to dual MFD, select that, and as you can see on the left hand side, we got a maintenance option over there. So we'll go back out of this, go to maintenance data pages, and we want to select chapter 71 EPCS, engine performance control system. So right now you can see our engine performance control page. We do not have any power going to our EECs, which is why we opened up a second window. So if we take the selector knob, we'll turn the big one, there you go, now select it. So now we'll go into maintenance control pages, miscellaneous system controls, and we're going to energize engine number 1 for this test. So now you'll see we have all our values for engine 1, and you can see our thrust lever angle, the third line down on the left hand side, which is 36.2 degrees, which is at idle. Via this connector here, down to our two connectors down in the forward nose wheel well. And then the power cord for this can get plugged in behind the first officer's position. It's a regular 3-prong, 110, 400 hertz, and we can turn our box on at this point to power. What we're seeing here with all these switches in the LED position is all 9 switches on our auto throttle switch pack at idle are normally closed. When we advance the throttle to our first reading of 44 degrees, we're going to see switches 1, 2, and 3 translate to normally open once we advance the number 1 throttle. The key behind this is to do this slowly so that we can see if we've got any bad switches. Our readings should go from normally open to normally closed to normally open without hesitation. We should go from amber to red immediately at 44 degrees on our thrust lever angle up there. Stop at the first one. So we already got S2 and S3. Change states from normally closed to normally open at 43.5, which is within allowable limits. We're allowed 44 plus or minus 2. Notice the S1 has not transitioned yet, so we're going to keep advancing the throttle until that one transitions. And notice we got a nice clean change from normally closed to normally open, and we are now at 44.9 degrees thrust lever angle, which again is within limits, 44 plus or minus 2 per the AMM. So that is our first 3 switches. You can bring the throttles back down to idle. We should see a nice transition from normally open to normally closed. There we go. There we go, and there we go. And you can bring them all the way down to idle. So the first thing we'd like to do is we want to make sure our switches are transitioning from normally closed to normally open. 1, 2, and 3 are supposed to transition at 44 plus or minus 2, but for this purpose, we just want to make sure they make and break cleanly. So I'm going to push the throttle forward. You can see all 3 of them instantly changed from amber to red. They went from normally closed to normally open, and then back down, they all instantly transition from normally open to normally closed. Nice and clean both ways. So once I've established that I'm getting a good transition point, I can switch to meter. I've got my auto throttle switch selected to 1, and then I'm going to go to test, and I'm going to look at the voltage drop, or the voltage across the normally closed contacts, because my throttles are at idle, which right now is 0.002, 2 millivolts. I'm going to push the throttles up again. You'll see a slight transition as I hit my transition point. That's my normally open voltage drop across my normally open contacts. I'm going to record those values, and when I come back to normally closed, I want this to match my starting point on normally closed. So I started out at 0.002. I have now transitioned, but I want to come back to closed, and I want to see the same 0.002. That's going to be the first value is the normally closed, 0.002. I'm going to transition to open and then back to closed. And my second value is going to be 0.002, and my delta value is going to be 0. That's a good switch. This is an example of a bad switch. I want you to focus on S6. When I pull the reverse lever back, S6 should transition at 32 plus or minus 2 degrees. And the key is you want to move the throttle slowly. Right there, my switch is neither closed nor open. Neither light is on. That's a telltale sign of a bad switch. If you look at S5 and S4, you'll see that they transition nice and clean. But you'll see anomalies with S6. Right there, neither switch is on. The switch blinked before the red light came on. The key is you want to do it slow. Again, it failed. I call it no man's land. We're neither closed nor open. We could try cleaning this switch to see if it works. A lot of times when you see this type of failure, replacement of the switch pack is recommended. So to clean S6, what we're going to do is reverse lever back down. We're going to switch to S6 here, and we're going to go to the clean. We'll switch this to meter, and we're going to go to the clean function, and we're going to cycle this thrust reversal lever back and forth to cycle this S switch to put current through it to clean the switch, the contacts. Again, we want to do this approximately 10 times. All right, after we've done it 10 times, we're going to go back to test. We can switch this back to LED. That's how we determined we had a failure to begin with. And again, we're going to move our reverse thrust lever slowly back and forth. And you can see now that the S6 is transitioning the way it should. To verify that we've got a good fix, we want to go to meter. We're still testing S6, but we're going to check the voltage drop across S6 now. This is in a normally closed position. Again, we want to wait 10 seconds for our values to stabilize. All right, our starting point for S6 is normally closed 0.002, 2 millivolts. There's our transition point. Our normally open contacts are 2 millivolts. Go back down to normally closed. It returns to 0.2 millivolts and back to normally open. Looks like we've got a good clean switch now.
.2 in range, S1 with it, 44.6 all within range, and smooth transition. These are all good switches.